Hello everybody, my name is Ajinkya Kulkarni and today I am here to discuss about elongation in members which are subjected to axial load. We will find the change in length of the members which are subjected to axial load. So I have taken two cases. That case 1 corresponds to tapering bars with axial load and case 2 corresponds to bodies under self weight. So we are going to analyze both of these situations with the help of this formula. Delta L is equal to PL by AE. This delta L is nothing but elongation of a rod of constant cross section. L is the length of the rod, P is the applied axial load, A is cross section area and E is the modulus of elasticity or Young's modulus. So the approach remains the same for all the four cases. Two cases from tapering bars and two cases from self weight. The approach remains the same. We will take an element and we will apply this formula to that element and then integrate over the entire length of the body. Now coming to first bar with circular cross sections. So we know that if we put the value of A as pi by 4 d square, so you will get the elongation of a circular bar. Now let us see how we can get elongation of tapering circular bar. So I have a tapering circular bar of length L, greater diameter d and smaller diameter as small d, and I have taken a small element of length dx at a distance x from the smaller end. So the net, this is the L, that is the length of the entire body. Now forget about this integral sign. Now we will just concentrate on elongation of the small element. So forget about this capital delta L and this integration sign. So if we put this formula, if we use this formula for the small length, so length of the element L is nothing but dx, P is the axial force, you can see. So P is the axial force and A. Now A corresponds to area of this element. If now by similar triangles we can get the diameter of this section as d plus d minus d by L into x. So this becomes the area of the element, that is pi by 4 d plus d minus d by L into x the whole square, and E remains the Young's modulus. Now if I integrate this over the entire length and I find the value of the integration, it comes out to be PL by pi by 4 d dE. So this is nothing but elongation of a tapering circular bar. Now coming to the second, that is the next approach. We will apply the same approach, and for the rectangular cross section we have a cross section of width A which is changing from A to B, from big end to small end. Then we have thickness of the element as T which is remaining constant throughout the length. Then I take the element at a distance x, the width of the element is dx, and apply the same logic. So and then I get the elongation as PL by A minus B into T upon log A by B into E. So this is the formula for elongation of length for a rectangular tapering bar. Now I come to case 2, that is ball weight, that is self weight. So we are going to analyze the elongation of bar which extends due to its own weight. So let us say this is the bar which is of circular cross section. It might be also of prismatic cross section. The area of constant we are going to take it as A, whatever it may be. So we have over here L, that is the length of the bar. From the bottommost section we take Y, at a distance of Y we take an element dy and do the same analysis. Forget about the integral sign now. So we get elongation of the bar is equal to PL by AE. Here P is equal to rho into A into Y. Now A into Y corresponds to volume below the element, and this is the unit weight, that is weight per unit volume of the bar. So if this corresponds to the entire force, that is P. dy is nothing but the length of the element, that is nothing but this L. Cross section area is constant, so not to worry. So cross section area remains constant, and E is the Young's modulus. So if you solve this integral, we get rho L square by 2E. So this is the value of elongation due to self weight of a prismatic or a circular bar. Now lastly, coming to conical piece under its own weight. So on similar grounds as of case C, we can get this thing. So here we have taken an element at a distance y, and the length of the element is dy, and found out the magnitude of elongation of the small element, and then we integrate over the entire length. Okay, so this gives you delta L is equal to rho L square by 6e. So with this I would like to end today's presentation. Thank you.